Good day. Today, we are now moving on to the Unit 5, Lesson 2, the quantitative aspects of precipitation reaction.
But first, what is precipitation reaction?
Precipitation reactions occurs when cations and anions in aqueous solid combine to form an insoluble ionic solid called a precipitate. Examples is the rock formations in El Nido, Palawan. So the rock formations are made of limestones which have deposited throughout the years. So limestone is composed of calcium carbonate rock crystal. Before delving deeper into this discussion, let us first know the two learning objectives that we hope to achieve at the end of this lesson. The first one is to determine the limiting and excess reactants in a precipitation reaction and to determine the amount of solid precipitate formed from a given concentration of aqueous reactants.
In the last lesson, we have talked about the qualitative assessment of determining whether product is soluble or insoluble using the solubility rules. Although this information is helpful in qualitative analysis, it is incomplete if you do not know the amount of insoluble product that is expected.
For this discussion, we will focus on the quantitative aspects of precipitation reactions. So now, without further ado, let us dive into our discussion.
For example, if we mix 5.0 ml of 0.50 mole SrCl2 and 10.0 ml of 0.20 mole Na3PO.
From the preceding lesson, it was elucidated that the resulting products of this reaction comprise of Sr3PO42 and NaCl, which is an insoluble precipitate.
And compute the anticipated quantity of Sr3PO4 that will be generated from the reaction. As you've gathered from earlier sessions, the project amount of product is termed the theoretical yield.
First, when determining the theoretical yield, it is crucial to establish the balanced molecular equation as a primary step. In our previous example, the balanced molecular equation is given as follows. You know that establishing the balanced molecular equation is essential because the calculation of theoretical yield relies on the stoichiometric ratio between the reactants and the product. It is the mole ratio between the reactants and products in a given reaction. It is determined by utilizing the coefficients of the reactants and products as indicated in the balance equation. For example, in the given equation above, the stoichiometric ratio of SrCl2 and Sr3PO42 is 3:1, while of Na3PO4 and Sr3PO42 is 2:1.
Step 2. Determine the limiting reactant. Remember that the limiting reactant is the reactant that is entirely consumed first in a chemical reaction, thereby restricting the amount of.
The limiting reactant is determined from the given amount of starting materials. The moles of each reactant must first be calculated. It is calculated through N equals M times V, where M is the molarity and V is the volume in liters of the solution.
In our example above, the initial amount of SrCl2 is 5.0 ml of 0.50 mole, while that of Na3PO4 is 10.0 ml of 0.20 mole. Therefore, the starting materials in our example are 2.5 times 10 to the power of negative 3 moles of SrCl2 and 2.0 times 10 to the power of negative 3 moles of Na3PO4.
If we begin with 2.5 times 10 to the power of negative 3 moles of SrCl2, it would necessitate 1.7 times 10 to the power of negative 3 moles of Na3PO4 for a full reaction.
However, our initial amount of Na3PO4 is 2.0 times 10 to the power of negative 3 moles. Consequently, we can infer that Na3PO4 is in excess, while SrCl2 serves as the limiting region.
Solving for the theoretical yield, use this formula. MPPT equals NLR times stoichiometric ratio times FWPPT. MPPT equals mass of the precipitate produced by the reaction, and LR equals moles of limiting reactant, and the FWPPT equals formula weight or molar mass of the precipitate. In our example, we use the starting amount of SrCl2 since we have identified it to be the limiting reactant. Thus, we expect 0.38 grams of Sr3PO42 to form from the reaction provided that the amounts of starting materials are given.
Step 4. Calculate the amount of excess reactant. SrCl2 is the limiting reactant. Therefore, Na3PO4 as the excess reactant.
To determine the amount of excess Na3PO4 left after the reaction, we must first calculate the amount of Na3PO4 that consumed by SrCl2. So, NXR3 consumed equals NLR times stoichiometric ratio, wherein the NX3 equals moles of excess reactant that got consumed by the limiting reactant, and NLR is the moles of limiting reactant. Based on our calculation, the limiting reactant SrCl2 necessitates 1.7 times 10 to the power of negative 3 moles of Na3PO4 for a complete reaction. However, the initial amount of Na3PO4 is 2.0 times 10 to the power of negative 3 moles. Consequently, we can determine the number of moles of the excess reactant Na3PO4 remaining after the reaction as follows. From the given of this equation, we have AgNO3. So, ang niyahang mole is 0.50 m. And then, ang niyang volume is 25 ml. So, since ang pagkuha na formula ana niya is kailangan nakaliter, ato siyang i-convert. So, 1,000 milliliter is equal to 1 liter. So, ito siya i-divide. Ang makuha na to is 0.025 liter. And then, in getting put for NaCl, so for NaCl, we have mole is equal to 1, and then the volume is 10. Same case, i-convert kahapon na to, 1,000 ml over 1. Then, divide, the answer would be 0.010 liters. The first step in solving is to first write the balanced molecular equation. So, AgNO3 plus NaCl reacts to AgCl plus NaNO3. As you can see, it is already a balanced equation. The second step is to determine the stoichiometric ratio of the reactants. So in the balance equation, 1 mole of AgNO3 reacts with 1 mole of NaCl. Therefore, the stoichiometric ratio of AgNO3 to NaCl is 1:1.
But remember, don't hesitate to call on me for anything. Like you said, a human being, I'm going to make you take that chance. Things have been different for me ever since I met Hildy. I've never met anyone quite like her.
Step 3 is to calculate the number of moles of each reactant using in the equation. So NaGNO3 equals M times V equals, iguro nimo siya i-substitute, so may tabaan na niya 0.50 M times 0.025 liters is equal to 0.0125 mole. The next one is for NaCl. It's the same formula lang imuang gamiton, which is M times V. So substitute 1M times 0.010 liters is equal to 0.010 mole. Operating amount daw sa AgNO3 is 0.0125 mole, and then ang stoichiometric ratio diba niya is 1:1, so meaning kailangan po na 0.0125 mole ang starting reactant para sa NaCl. But since atong pag-solve atong nakuha lang is 0.0110 mole of NaCl, therefore sa kanina equation nakabalaan nato na si NaCl ang atuang limiting reactant, because as you can see naga-limit lang siya. After nakuha na to ang example na 1, we will now move on to the try it number 1 para mabalaan nato kung na-apply ba na to ato ang na-learn sa example number 1. First, kailangan sa nato i-identify itong given. So for AgNO3, ang mole niya is 0.163 mole. And then, ang niyang volume is 27.8 milliliters. So, kailangan man siya na mahimong liters, maong i-convert na to siya, i-divide na to siya into 1,000 milliliters. So, pag-divide ana, ang makuha na to na answer is 0.0278 liters. So, the same lang po na itong buhaton para sa Na2S. So, ang mole would be 0.134, and then atong volume would be 40.5 milliliters. So, kailangan man po siya na i-liter na po, i-divide na po siya sa atong 1,000 milliliter, katumbas sa isa ka liter. So, the answer would be 0.0405 liters. First step is we need to know if ang given ba is nakabalance na ba siya daan. So, Na2S daw is made to react with AgNO3. So, isulat na to siya. Na2S is made to react with AgNO3. So, since precipitation man siya, and then ionic po na siya, so ito lang siyang i-distribute based sa itong nabalaan sa ito ang previous discussion. So, NaNO3, then ito na siya ibaba since delete na ito siya. AgS. So, seeing alone from this equation, ato na siyang makonclude na this is a balanced equation. Makita to si Na2, balance din Ia, balance dira, and then si sodium, balance, Ag, balance, and NO3, balance. So, this one is a balanced equation. The next step is we need to get the stoichiometric ratio of the product to the reactant in a given equation. So we already know na yung stoichiometric ratio is 1:1. So next is we need to calculate the number of moles of each reactant. So N is equals M times V equals to 0.134 M times 0.0405 liters is equal to 5.43 times 10 to the power of -3 mole. And then for number of Ag and O3, we have M times V is equal to 0.163 M times 0.0278 liters is equal to 4.53 times 10 to the power of -3 mole. So since I've already said the stoichiometric ratio is that the product reactant should react to the one coefficient of the reactant. So si product daw dapat exactly the same na siya sa atuang reactant. And then makita na to diri na kanisi patong product and then si reactant is totally the same ang iyahang values. Therefore, ang limiting reactant in this equation is the NaGNO3. So in this equation, for try it number 1, the AgNO3 is the limiting reactant. However, there would be confusions in getting the stoichiometric ratio. So all you need to remember that it is a mole ratio of between the mole ratio between the reactants and the product and the product in a given reaction. So remember, ratio lang na siya sa reactants and products sa isa ka given equation. So for example number 2, we need to determine first the stoichiometric ratio of the limiting reactant to the precipitate in the balance equation. So we already know that the stoichiometric ratio for AgCl and NaCl is 1:1. So take note that we will be needing this in solving for the theoretical yield of the precipitate. So for step 2, so this is the step 1. For step 2, we need to calculate the theoretical yield. So we already know that the formula for that is M, since our precipitate is AgCl, could be NLR times stoichiometric ratio times FW/PPT. So this is the number of the limiting reactant, and the limiting reactant for the sample number 1 is NaCl, and ang iyahang number for that is 0.010 mole of NaCl. And then the stoichiometric ratio will be 1. So we will transform it into fraction. So mahimo siyang 1 mole of AgCl and then 1 mole of NaCl. Next is the formula weight for the precipitate form. So, dali na to siya ibutan since dili na tayo sa space. So, ang formula weight niya is 144 grams per mole AgCl. So, giun sa pagkuha aning 144. So, after finishing this, I will explain it later. Giun sa pagkuha aning 144 mole AgCl. So, in solving that one, we would get, so this would be the total answer. The total answer would be 144 grams of AgCl. So, giunsa pagkuha ani niya. So, gibuot ang anak niya is simply gi-times sila tanan si 0.010 mol, si 1 mol over 1 mol, and then si 144 g mol. So, how did it get so grams? So, ang gibuot lang anak niya is atuwa siyang gi-crush out. So, mol NaCl, and then mol AgCl. So, mabilis atuwa is si grams. So, asig gikan si AgCl. So, since ang gipangita man nato is to calculate the theoretical yield of the precipitate form, and then the precipitate for this equation is the AgCl, so mo na siya for the complete answer. So, 1.44 grams of AgCl. So, going back, and how did we get the 144 grams per mole is going back to the basics. So, AgCl, so you need to first get their weight. So, the Ag is only 1 lang man siya. Since 1 lang man dere, then 1 dere, and then si Cl is 1 pod. Si Ag, kina siya ay 108 grams, and then si Cl is na ay 34 grams. So, answer ana niya is 108 and then 34. So, kani siya mag-base ta sa tuang periodic table, and since naka-decimal mo to siya, to lang siyang whole number so that naatay uniform answers. So, 108 plus 34 equals 144 g mol. So, there would be in AgCl na atay 144 grams per mol. So, for try 8 number 2, since kabalo naman ta na kailangan na tukaon tong formula weight para sa tuwang precipitation, yun na to siya pagkuha para sa number 2 na try 8. So, formula weight of Ag2S, so Ag2 and then ang SK1, so 2 times 108 and then si S is 32. So, ito siyang times 216, so 108 times 2 is 216, and then 32 times 1 equals 32. Ato na siyang i-add, ang answer would be 248 grams per mol. Next thing to do is kuhaon nato tong stoichiometric ratio, which is ang ato ang precipitate and then ang limiting reactant ng mga coefficient. So ang answer would be 1:1 gihapon. The second thing that we will need to do is to get the MNA2S. So ang formula is NLR times stoichiometric ratio times formula weight of the precipitate. And then, ang number of limiting reactant is 4.53 times 10 to the power of negative 3 gikan sa tuwang last equation, and times ang atong stoichiometric ratio, which is 1 mol Ag2S over 1 mol Na2S, times the formula weight of the precipitate, which is 248 grams per mol. So the final answer for this equation would be 1.12 grams of Ag2S. So makuha na na siya by crashing out lang na siya sa mga similar terms. So for clarifications, in case there's some confusions between stoichiometric ratio and then stoichiometric ratio for theoretical yield, is ang ratio for stoichiometric ratio is the coefficients between the products and then the reactants in a given equation. While for theoretical yield naman, it is a ratio between the precipitate and then the limiting reactant. So for example number 3, we would need to determine the amount of excess reactant remaining after the precipitation reaction. So to get this is first step is that we would need kailangan nato pangitaon ang na-consume. So to get that is to NaGnO3 consumed is equal to N number of limiting reactant times the stoichiometric ratio. So the number of limiting reactant, again from the previous example, is 0.010 mole of NaCl. And then, the times na siya sa stoichiometric ratio, which is 1 mole of AgNO3 over 1 mole of NaCl. So, to answer that one, the answer would be 0.010 mole. So, wala ni siya ang na-consume. Next step is to need to subtract the mole of excess reactant that was consumed from the initial number of moles in the starting material. So, we'll get that. The formula would be NaGnO3 remaining and then kailangan lang na to i-subtract ang precipitation, which is ang number of the precipitate, which is the 0.0125 mole ni siya si AgCl. Then ato siyang i-minus sa katong atoang nakuha na product kanina, which is the 0.010 mole, since mao to ang atoang consumed. Kaya kailangan mo na to kuhaon ang amount sa excess reactant remaining after the precipitation reaction. So to get that, we just need to subtract this one. So 0.0125 mole minus 0.010 mole, the answer would be 0.0025 mole. So the final answer for example number 3 is this one. Therefore, the amount of excess reactant is 0.0025 mole. The first step, we would need to calculate the moles of excess reactant that was consumed by the limiting reactant. So for Na2S consumed, ang atong formula for that is number of limiting reactant times the stoichiometric ratio. So in substituting for number of limiting reactant, 4.53 times 10 to the power of negative 3 times the stoichiometric ratio, which is 1 mole Na2S over 1 mole AgNO3 is equals to 4.53 times 10 to the power of negative 3 mole. For the second step, we need to subtract the moles of excess reactant that was consumed from the initial number of moles in the starting material. So, Na2S remaining is equal to 5.43 times 10 to the power of negative 3 minus 4.53 times 10 to the power of negative 3 is equal to 9 times 10 to the power of negative 4 mole. Therefore, 9 times 10 to the power of negative 4 mole is the amount of excess reactant for this equation. That would be all for the quantitative aspects of precipitation reaction. I hope you have learned something from our discussion, and I hope to see you again.